Welcome to Lesson 7.6 Project Integration and Deployment. Learning Objectives. Azinan Vexis Ubina Alice and practice. You'll master these techniques quickly. This is where everything comes together. Over the previous 5 lessons, you built 5 distinct production AI applications. Now you're going to wire them into a single unified platform, shared infrastructure, centralized monitoring, and a real deployment pipeline. This is what separates a collection of models from an actual production system. Budget about 90 minutes for this one. It's advanced material, and it assumes you've completed lessons 7.1 through 7.5. Integration Overview. The Let's Integration Overview. Fires Natsis Astomanskaitetio and the Nets Ananias Integration Overview. Here's the full architecture of what you're building. At the top sits a fast API gateway, the single front door for every client request. Behind it, an Nginx load balancer distributes traffic across your services. A JWT-based auth service sits in line, so no request reaches a model without being verified first. The 3 core AI services, the support bot, code docs generator, and legal analyzer, each run on their own dedicated ports. They share 2 pieces of infrastructure: a Redis cache for fast repeated lookups, and a Postgres database that captures logs and analytics. At the bottom of the stack, Prometheus scrapes metrics from every service, and Grafana turns those metrics into dashboards you can actually read. The reason this architecture matters is that each layer has a single clear responsibility. When something breaks, and in production, something always breaks, you know exactly where to look. Phase 1. Unified API Gateway. The gateway is the brain of this platform. This fast API application receives every incoming request, authenticates it, routes it to the correct AI service, and optionally serves the response straight from Redis cache without ever touching the model. The service registry is the key data structure here. It maps each service name to its internal URL and a flag indicating whether responses should be cached. Notice that the medical diagnosis service has caching disabled. That's intentional. You never want a cached diagnosis served to a patient whose condition may have changed. Authentication is a simple token verification function. In production, you'd swap this for a proper OAuth 2 flow, but the pattern is identical. Each endpoint follows the same shape. Verify the token, check the cache, forward to the service, store the result, return the response. Uvicon serves the whole thing on port 8000, listening on all interfaces. When it starts cleanly, you'll see a confirmation line in the logs. That's your signal that the gateway is ready to accept traffic. Phase 2. Containerization with Docker Compose. Docker Compose turns this multi-service architecture into a single command. Each service gets its own container, the gateway, every AI service, Redis, Postgres, Prometheus, and Grafana, all defined in one file. The gateway service is declared first. Its environment variables, Redis _ hosty, Postgres _ host, tell it exactly where to find the shared infrastructure. Each AI service like support bot and legal analyzer specifies its own model path and GPU device assignment, so you get clean resource isolation even when 2 models are running on the same machine. The depends _ on directive is doing important work here. It prevents the gateway from starting before Redis and Postgres are ready to accept connections, a race condition that would otherwise cause cryptic startup failures. To restart. Unless stop policy means any service that crashes will automatically recover without you having to intervene. Redis and Postgres both mount persistent volumes, so your data survives a container restart. This entire file is your deployment artifact. Version control it like you would application code. 4 commands cover the entire life cycle of this platform. The first, Docker Compose up deity, starts every service in detached mode. They run in the background and keep running after you close the terminal. Watch the output carefully. Each service should report started or healthy. Any service stuck on starting is worth investigating immediately. Docker Compose PS gives you a snapshot of what's running right now, container names, ports, and status at a glance. Docker Compose logs, fire gateway streams the gateway's logs in real time. This is your primary debugging tool during initial deployment. You're looking for successful startup messages and the absence of connection errors to Redis or Postgres. When you're expecting high traffic on the content moderator specifically, Docker Compose up Narcissus scale content moderator =, 3 spins up 3 instances of that service. The load balancer distributes requests across all 3 automatically. Docker Compose down cleanly stops and removes every Run this when you're done testing. It leaves no orphan processes behind. Phase 3. Unified Monitoring Dashboard. This Prometheus configuration is what gives you visibility into the entire platform. The global scrape _ interval of 15 seconds means Prometheus polls every target every 15 seconds, frequent enough to catch transient spikes, light enough to not become a performance burden itself. Each scrape _ config job maps to a layer of the stack. The gateway job targets port 8000. The AI services job covers the support bot, content moderator, and the other model endpoints, all exposing metrics at the standard /metrics path. There's a dedicated job for Redis and a node exporter job that pulls GPU utilization data directly from the hardware. The reason you want GPU metrics in Prometheus is that model inference is GPU bound. If a service starts responding slowly, the first thing you check is whether GPU utilization has spiked to 100%. That tells you immediately whether you need to scale horizontally or whether something else is wrong. The Grafana dashboard JSON defines 6 panels, and each one answers a specific operational question. Requests per second tells you whether traffic is growing, stable, or dropping. P95 latency shows the response time that 95% of your users actually experience. The median can look fine while the tail latency is silently hurting real users. The error rate panel is your early warning system. A sudden uptick in 5xx errors before you've noticed anything else is the signal to start investigating immediately. The 2 GPU utilization panels track your hardware. If utilization is consistently near 100%, your models are saturated and you need more capacity. If it's near 0, something upstream, the gateway, the cache, a network issue, is preventing requests from reaching the model. Cache hit rate tells you whether your Redis investment is paying off. A rate below 70% suggests your cache keys aren't matching real traffic patterns. Service health is the simplest panel. Green means the service is responding. Red means it isn't. This is the panel you look at first thing every morning. Phase 4. Integration testing. Why need Qt T2 time? Analysis and practice. You'll master these techniques quickly. Before you declare this platform production ready, you need proof that all 5 services actually work together through the gateway. This integration test script does exactly that. It fires a real post request at each service endpoint, checks the HTTP status code, and prints a snippet of the response. The script uses a single base URL and a single auth token, which means it's testing the full request path, token verification in the gateway, routing to the correct service, model inference, and response serialization. If any of those steps is broken, the test will surface it. After testing all 5 services individually, the script hits the health endpoint and the metrics endpoint. The health check confirms every downstream service is reachable from the gateway. The metrics response shows cache hit rates and per service latency, the same numbers you'll see in Grafana, but available programmatically. Run the script after every deployment. If all 5 services return 200S and the health check is clean, you're good to go. Results and platform metrics. Here's what this platform actually delivers against real production targets. Gateway overhead came in at 12 milliseconds against a 50 ms budget. The routing and auth layer is adding almost no perceptible latency. Cache hit rate landed at 82%, well above the 70% threshold, which means more than 4 out of 5 repeated requests never touch a GPU. Platform uptime reached 99.97%. That's roughly 2 hours of downtime per year, which is enterprise-grade availability. Concurrent throughput hit 680 requests per second against a 500 target, and service availability across all 5 models held at 90. These numbers aren't theoretical. They're what you get when you combine proper caching, health check-driven restarts, and a load balancer in front of horizontally scalable services. The architecture earns the results. Zoom out and look at what 5 models running together actually mean for a business. The projected cost savings across all use cases run between $500,000 and $2 million annually, driven primarily by the reduction in human labor for tasks the models now handle. That human workload reduction is 60 to 90% depending on the use case. Response times that previously took hours now take seconds, a 99% plus improvement. Every response is consistent with policy because the model doesn't have bad days, and the platform can process millions of requests daily without adding headcount. That's the compounding value of getting the infrastructure right. Key takeaways. 5 architectural principles made this platform work. A unified gateway gives you a single point of control for routing, authentication, and rate limiting. You make that change once and it applies to every service. Shared infrastructure means Redis and Postgres aren't duplicated per service. They're provisioned once and shared, which cuts operational overhead significantly. Service isolation means each model runs in its own container. If the legal analyzer crashes, the support bot keeps running. Horizontal scalability means adding capacity is a single Docker Compose scale command, not a re-architecture. And full observability means you have metrics, logs, and health checks from the first deployment, not bolted on later when something goes wrong. The patterns you've applied here are patterns you'll use in every serious production system. The API gateway pattern centralizes the cross-cutting concerns, auth, rate limiting, routing, so individual services stay focused on their one job. Treating each AI model as an independent microservice means you can update, redeploy, or scale any single model without touching the others. Aggressive caching is powerful, but the medical service taught you the critical exception. Never cache responses where staleness has safety implications. Monitoring from day one means you have a baseline before anything goes wrong, which makes anomalies obvious. Docker Compose handles local development and staging deployments cleanly, and health endpoints on every service give the platform the information it needs to route around failures automatically. Module 7 complete. You've now built 5 production AI applications and unified them into a single deployable platform. The customer support chatbot resolves 82% of tickets without human intervention. The code documentation generator scores 4.2 out of 5 on quality evaluations. The legal document analyzer extracts information with 93% accuracy. The medical diagnosis assistant hits 87% accuracy with full safety alignment. The content moderation system runs at an F1 score of 0.96, with all 5 run behind a shared gateway with caching, monitoring, and automatic recovery. Module 8 is where these projects meet true production scale, Kubernetes orchestration, advanced monitoring pipelines, CI/CD automation, and deep performance optimization. Everything you've built here is the foundation for what comes next. This architecture diagram shows the request path from client to storage. Client applications, web, mobile, or direct API consumers all enter through the API gateway. From there, the load balancer distributes traffic across 3 LLM workers, each capable of running inference in parallel. This horizontal layout is what allows the platform to handle concurrent requests without queuing behind a single model instance. Notice that the load balancer also has a path to the Redis cache. Requests for data that's already been cached never reach the workers at all. They return immediately from Redis. Only cache misses proceed to inference. PostgreSQL sits beneath worker 1 as the persistent store for logs, user sessions, and analytics. The key insight here is that the cache and the database serve completely different purposes. Redis optimizes for speed on repeated queries. Postgres optimizes for durability and queryability of historical data. The REST API surface for this platform follows the OpenAI compatible schema deliberately. That means any client already written for the OpenAI API works with your self-hosted models without modification. The 2 post endpoints are the workhorses. Post/v1/chat/completions handles multi-turn conversations with a messages array. Post/v1/completions handles raw text completion for single prompt use cases. Post/v1/embeddings generates vector representations essential for similarity. The get endpoints handle discovery and operations. Get/v1/models lists every model currently loaded on the platform. Get/v1/models/model_id returns the metadata for a specific model. Its content. Get/health is what Docker and Kubernetes use to decide whether a container is ready to serve traffic. Get/metrics is the Prometheus scrape endpoint. It's what feeds your Grafana dashboards. Delete/v1/sessions/id clear clears the stored conversation history for a session, which matters for privacy compliance and for users who want a clean slate. This monitoring dashboard covers a 24-hour window, and the 3 panels tell a coherent story about your platform's health. The top panel, requests per minute, shows a gradual upward trend. That's healthy organic growth. What you're watching for here is sudden vertical spikes, which indicate either a traffic surge that might require scaling or a retry storm caused by a downstream failure. The middle panel tracks P95 latency, the response time that 95% of requests fall under. This is the number that matters for your SLA. The median can look perfectly fine, while a small percentage of users are experiencing multi-second delays. P95 catches that. Any sustained increase in this line warrants investigation before users start filing complaints. The bottom panel shows error rate against the error budget line. The budget line is your acceptable ceiling. Staying consistently below it means your reliability target is intact. A spike that crosses the budget line is an incident, not a warning. The moment you see that, you start pulling logs from the gateway and the affected service simultaneously. This deployment pipeline is the process that takes code from your editor to production in a controlled, repeatable way. It starts with a code commit, the trigger that sets everything in motion. From there, unit tests and model evaluation tests run automatically. These catch regressions before they ever touch a running environment. If tests pass, the pipeline builds a Docker image. This is what makes deployments reproducible. The image captures the exact code, dependencies, and configuration at that commit. The same image runs in staging and production, which eliminates the classic works on my machine failure mode. The staging deployment runs the new image in an environment that mirrors production. Same infrastructure, same configuration, real traffic patterns from a subset of users or synthetic load. Smoke tests then verify that the critical paths are functional. The gateway responds, the models load, health checks pass. Only after smoke tests pass does the pipeline promote to production. Post-deployment monitoring then watches for any anomalies in the first 30 minutes, the window when most deployment-related issues surface. This pipeline is what makes it safe to deploy frequently without fear.